Welcome everybody to the ThermTest demonstration corner. Today we're going to talk about the MP-1 Transient Plane Source Slab Module. Both the use of it, the improvements, the advancements of the method. But before we do that, it's sort of custom here to just talk a little bit about the demonstration corner, what it is and what we do with it. So this is our demonstration corner full of our equipment, ready to use all the time for doing demonstrations and training. In our corner is our GHFM for ASTM E1530. This is for measuring complex materials, heterogeneous, in the high range, mid-range to high thermal conductivity, from 0.1 to 100 watts per meter Kelvin up to 300 Celsius. This is guarded. It's called a guarded heat flow meter. That's what enables it to measure small format materials. We'll do a demonstration on that, of course, another day. This is our heat flow meter, which comes in different internal dimensions for measuring insulation and construction materials. This follows ASTM C518 and related international standards. And then coming back around to the other side of the demonstration corner is the transient hot wire. This is the THW-L1. This is the ability to measure liquids and pastes and PCMs from cryogenic temperatures up to 300 Celsius and 20 or 35 bar. Why that's important is for measuring past boiling points. This follows ASTM 7896. It's a transient hot wire. And this is our basic transient plane source, TPS-2, for measuring polymers, metals, insulators up to metals. The two range options on it are 100 watts per meter Kelvin and 500 watts per meter Kelvin. The popularity of these two, primary method for measuring liquids and primary method for measuring solids, and I should say that this method follows ISO 22007-2. The popularity of these two coming together, primary methods for liquids and primary methods for solids, was really the motivation for why we designed the MP-1 from the ground up. So we looked at what was available in the market and the needs of our customers and advanced both of these methods dramatically. So the MP-1, it is basically stands for measurement platform, and we configured it to really allow a variety of methods. So the additional method that you can add to this, besides transient plane source, transient hot wire, is the transient line source, which we're not talking about today. Every MP-1 comes with a 4-channel switch, and we'll be using those channels today because we're going to set up an experiment inside the optional temperature module, which we call temperature platform. We're going to set up an experiment inside the TPS temperature platform. This can go from different ranges of low temperature. This device is 0 to 300 Celsius, but we have options for all the way down to cryogenic. This is our temperature platform for transient hot wire. That module can go from cryogenic, again, depending on the lower temperature options you need, up to 300 Celsius in different pressures. And then we have room temperature configuration. So typically channel 1 or port 1 is used for room temperature, but we usually have extra ports in the back that are available. So today we have 2 temperature platforms plugged in, and port 1 in the front is 1 room temperature sample holder. The second sample holder is plugged into port number 4 in the back. So currently 1 controller, and every MP-1 comes with those channels. It's the basic configuration. You can expand it. So you could have a number of sample holders all at room temperature. You could have many more temperature platforms all configured with the same controller. And these are configurable, so as you can see, they separate out, and you can expand as you need it. So we're going to talk about the transient plane source slab module, which is designed for measuring thin conductive materials. The traditional use of it is for when the thickness of your sample is thin and you can't satisfy penetration depths on the thickness. So what the slab module does is it isolates the thickness and looks at the heat propagation along the in-plane direction of the sample, which of course, if you have a sheet form, so it's again designed for conductive sheets, your greater dimension is in the slab or the sheet direction, radially. One of the advancements we have made for this method is to enable backing correction. So the isolation that I referred to, the insulation that we use to isolate the sample, enables us to account for and calculate the heat loss that is bleeding into the backing material, which enables us to measure lower conductivity materials. So the proprietary backing correction we have allows us to measure lower conductivity materials or materials with a greater resistance. So here we have peak. We'll show you some data we've measured on peak. We'll show you that data correlated to the guarded heat flow meter. This is Pyrex. We'll show you this experimental setup on Pyrex, as well as some data we measured on Pyrex. These are both traditionally lower than the slab module can use without the backing correction. The second advancement we have made on the slab module is the ability to measure asymmetric. So again, traditionally we sandwich the sensor between two samples. We're going to show you that. But with the proprietary advancement we've made on this method, we have the ability to measure a single piece of material with the slab module. So if you do not have two pieces, which is the traditional setup, two-sided or symmetric, and you only have one piece of material, we're able to measure that, and we'll show you that setup. So we're going to switch cameras to a close-up of the sample holder. So this is a view of our TPS sensor already configured in the adapter that is available. I invite you to look at previous videos where we talk about temperature range on sensors, temperature ranges of adapters. We're not going to go over that right now, but that sensor is inserted into the receiver and connected. There's a window that allows you to know that your sample is, rather your sensor is configured properly. So for sample setup, we're going to place in this case, the Pyrex we're going to measure symmetrically. We're going to place one piece on the bottom. And the sensor we're using in this case is 4617, or approximately 10 millimeters diameter. We can adjust the height of the sensor to account for different heights of material. The slab module allows you to measure basically down around 0.05 millimeters up to 9 or 10 millimeters thick. The thermal conductivity range for this method is traditionally around 2 watts per meter Kelvin up to 1800 watts per meter Kelvin, but with the use of the backing correction, it's closer to, the lower range is closer to 0.1 watt per meter Kelvin. So our configuration in this case, symmetric. We do need to place the isolation foam on each side of the sample, and then we're going to lower the top bar and set that up. So that's our setup for symmetric on these Pyrex samples, which will let us exercise the backing correction, which is XPS. And the second setup, and I'll share the software as the second step of this demonstration, but I wanted to show you the setup for asymmetric slab. So here we have 2 pieces of stainless steel. I'm going to remove one piece, and so the symmetric setup is backing or insulation, sample, and I've already previously measured the thickness. You need to know the thickness of each of your slab as well as the radius of each of the materials. They do not have to be round, they could be square or really any shape that has a flat sample. And we're going to isolate the sample. And I'm only doing finger tight in this case. So I'm going to back that off and just make sure I have that in the center. Again, you want to make sure your sensor is in the center of the material. So that's the asymmetric setup. For symmetric setup, we would do, one on the bottom, one on the top. That just makes sure that the sensor and the sampler are in good contact. So we're going to switch to the desktop and go over some data. Actually, we're going to set up an experiment first. So here's the screen of the MP-1 software. This is your home button, which shows everything that's plugged in. Again, previous videos would demonstrate what that means, but it self-detects everything that's connected to it, including the sample holders. This is our experiment setup page. We're going to do a symmetric test on a slab material. Here's where you would point to where you want to store the data. So here we've entered Pyrex 3DS, which stands for 3D slab. This is your serial number of your device, and where you can select the various devices that you want to measure inside of. So either room temperature or a temperature device. So in this case, we're going to do a room temperature and continue to the next screen. This is where you name your sample. You pick your backing type. This is XPS. This is the thickness of the sample, which I've previously measured and entered, 3.3 millimeters. And the radius of that material is 25 millimeters. The port that sample holder is plugged into is port 1. Again, it self-detects that, and it knows it's a TPS room temperature sample holder. The selection of the sensor model is automatic based off of the thickness. Now I've already run this, so the sensor that is used in the demo is already set up. But if I was unaware of what the sensor should be, that auto recommends the sensor use based off the thickness of the sample. I'm going to check the sensor. So this makes a electrical resistance measurement, a very brief one, to make sure that you have good electrical contact between the sensor and the contacts that are used for sensing. And that's a good. That measures the resistance, and if you mouse over it, it tells you what that resistance is. It compares the measured resistance with the expected value to tell you if it's good or bad. Temperature is automatic. Every adapter, every sample holder has the ability to measure the room temperature or the temperature that you're measuring in. Maybe it's in an oven, maybe it's in one of the temperature platforms. The TC range, this is our ITPS for measuring, for auto-selecting the parameters. I've already run that. In this case, we're going to run a 40-second measurement with a 100 milliwatts. Where do those parameters come from? That ITPS makes a continuous measurements and looks for the transient versus time temperature rise to ensure that the minimum temperature rise for a measurement is met and that the penetration depth is met. Both of those parameters tie into those expectations. The reason why I'm not running right now is because it takes a few minutes. So we'll just continue on. You can see the data on the output. Previous videos, we do run the ITPS. So you can sort of see how the automation works. And you can see the previous. So we're going to continue to the next screen, which lets me run a schedule. This is only at room temperature. So I'm going to add a single experiment at the wattage. So here's my 40-second test, 100 milliwatts. I'm going to do probably a little bit longer delay because this is a low conductivity material. I'm going to run 5 measurements, and I'll click Start Measurement. So that goes over to this schedule of experiments, and we can see that right now the event log, it's measuring the sensor resistance, and it's going to wait. I had pointed out for a 10-minute delay. It's going to wait 10 minutes before it runs the first experiment. So while it's doing that, I'm going to go ahead and set up my stainless steel, asymmetric. So we're going to pick the method. It's 3D disk source. I'm going to pick asymmetric slab. So this is the single-sided version of slab. I'm going to point it to a location for storage. I think today's 02. The sensor size we're using, again, I've already run the recommendation. This is stainless steel 304, and this is a asymmetric 3D slab measurement. Click Next. Measurement device is self-detecting. We're going to run a room temperature measurement. Stainless steel 304. The backing material is XPS. The thickness of the stainless steel is 3 millimeters. The radius is 20. I previously measured those. This is connected to port 4. As you can see, it's already detected that. I'm going to recommend the sensor size, 33171. Again, that's based off of the thickness of the sample. That's what I have set up. I'm going to check the resistance. So it's a required step to make sure that you don't waste time setting up an experiment, walking away if your sensor's not ideally configured electrically. Again, the ITPS is what you would run if you want to determine the parameters. We're going to run a 5-second measurement at 500 milliwatts. Now, from here, I'm going to do something a little different than I've done in other demonstrations. I'm going to show you the quick transient. So from here, I could go on and set up the schedule, but I could also run a quick transient. So this will let me do a very fast measurement to see the use of my parameters and see the output of that data, and we can look at that here, then set up a schedule and review some of the data. And then also we're going to set up the temperature platform for a slab measurement as well. So we're doing a little bit of different experiments to really show the diversity of the method. So there's an event log showing the test being run. The room temperature is 24 degrees. So this is not measuring the drift, it's only measuring a transient, so there's no recording of drift, which is part of our standard measurement when you run the schedule to make sure you have isothermal conditions. This is only running a transient as an estimation of your use of your parameters. While this is going on, please feel free to write the questions. If you have any questions in the chat box, we will have some time at the end, and as well if after the demonstration, if you want to write us with any questions, we're happy to answer them. So let's finish the test. Here's our transient of temperature rise versus time. It's doing the calculations. Once that's done, it'll give us a check of the quality indicators. So this tells us that all of our quality indicators are met. There's no red lights. Our residuals are nice and random. That tells us our fit is good, and we can continue. If we want to see that data, so this shows us the volumetric specific heat result from that experiment. We'll open this data, this early data, we'll open this up in the analysis and show you that data as well. We're going to click next. And we're going to run 5 measurements with a 10-minute delay with the milliwatts and start. So right now we have two sets of experiments on 2 channels that we're going to have data for later. We've already run the data. We can demonstrate that and demonstrate the thermal analysis. I'm going to switch back to the close-up and show you the physical setup on the temperature platform. So this is our temperature platform for the transient plane source. So this is a close-up view of the different stages of disassembly and assembly for a sample setup. This is our hood. This has a switch inside of it that detects that you have it off. If you have it off, it won't let you continue with your temperature work. That's just a safety. This is the outer cell, which is the cooling component. So everything all the cooling and the heating is within the same device. This is the cooling component of this proprietary device. This is the heating component. So those two work in opposing temperatures to give us very precise and automated control of temperature. This is our sample cell, our test area. This is the floor goes up and down to accommodate different thicknesses. So we're actually going to do, if we wanted to do bulk samples like this, so the biggest sample we can fit inside the temperature platform is a 40 millimeters by 20 millimeters in height. We have sample cells for this for pastes, powders, and liquids. Melt cells, there's a large number of different cells we can use inside of this. But if you're measuring just the solid, the largest is 40 millimeters in diameter by 20 millimeters in height. Of course, the sample can be smaller than that. That's just the maximum. So to accommodate the different heights of material, we want to make sure we lower the floor to accommodate it. So in this case, we're actually going to measure slab. So the slab configuration is going to be, as you see here, insulation, symmetric sample, which is 2 pieces of stainless steel, and insulation. And this leads us to why the backing configuration, or the backing correction I should say, is really important for a second reason. So it extends the lower range of the conductivity. Equally critical, it allows us to use different backing material to measure high temperature using the slab module. So if we were to use this, which is calcium silicate, as a backing material without slab correction, you would see 10 or 15% leakage, and your data would be affected by that. So even though this material is in the 14 watts per meter Kelvin region, that you would still have some leakage due to the higher conductivity. So XPS is around 0.03. That's our traditional backing. And as you go down in conductivity for a sample, you have the potential of getting leakage, which will affect your results. As well as you go up in conductivity of the backing, you can get leakage. So it has two purposes. It allows us to use a unique selection of materials for temperature and lower conductivity. So our configuration is going to be symmetric. And we want to lower the floor so that the top of the slab sample sits equal to where we're going to load the sensor. So I'm going to lower that floor a little more. That's pretty good. So now we're going to set up our sensor. In this case, we're using the exact same diameter, 6.4 millimeters radius, as we set up for the symmetric configuration on the bench. And to do that, you back off the knurled knobs, and there's 4 contact points that are underneath this peak adapter. We're going to insert that, and you can see, I'm sorry the camera angle doesn't let you see that, but there's a window in the back that lets you know that that is lined up. So there's only one way to insert it, and the probability of making those contacts is quite good. So we're going to tighten that equally so that we have good contact in all 4 points, and then repeat the process where our slab is the next piece, and our backing material, our slab insulation, is next. So that's our setup, and we're going to put everything back in reverse. So we're going to put the heating lid on. So we affix that on the sides first. And then we can apply a little bit of pressure to make sure that our samples come together tight. And then we put back our cooling lid, which again encapsulates, and so you have a completely surrounded heated cell with cold. So in this case, again, we can go down to 0 degrees up to 300. And this has no external cooling. The cooling from this comes from a really efficient thermoelectric pile. And then we put our lid back on, and that's the sample setup for the temperature platform for measuring slab. So we're going to go and we're going to set up another experiment. So we're going to do 3D disk source, symmetric, slab. We're going to point it to a direction. Now in this case, it is not asymmetric, it's symmetric. And we're going to select the temperature platform for the transient plate source. So when we do that, it shows the device. And we're going to put in the sample name. The backing material in this case is calcium silicate. The thickness is 3 millimeters. The radius is 20 millimeters. The port we're using is the temperature platform. We'll recommend the sensor size again. That's what we already used. We're going to check the sensor resistance. So it's the same function. It's just inside that adapter that's inside the temperature platform. So again, this confirms that the contact is good. And we're going to run the parameters that the ITPS would tell us, which is automation of parameters. And we're going to click next. Now here's where we can get into the control of this device for measuring temperatures. So I'm going to set up a multi-temperature schedule. So you can do an individual temperature like this, change it to 50 degrees, and it would automatically do that. I'm going to cancel that and do a range of items. So I'm going to run a temperature setup from 0 degrees to, let's say, 350 degree increments. I'm going to do 1 power, that's the 500 milliwatts at 1 time duration. 5 experiments at each temperature step with a 10-minute delay. I'm going to add that to the schedule. So it automatically builds our schedule. So we have 0 degrees, 50, 100, etc. And we will click next. So what that does is it automatically puts the configuration of the temperature steps associated with the temperature platform. Here's this. If you click on the experiment waiting to be run, it shows you the specific details of that setup. We can compress that. And now we have 3 experiments set up that are going to run at different stages, and you'll start to see the temperature change on the front of the temperature platform. I realize that I'm not showing the screen. Sorry about that. I'm going to go back just briefly and show that. Sorry about that. You know what? Here, let's. This is live, so I'm going to cancel that. I'm going to cancel that experiment. And so let's say you do something like that you want to redo. I'm going to right-click and copy to a new experiment. So it gives me an opportunity to show that if this ever happens to you, it's very easy to repeat a process. So all these parameters are already in configuration from that experimental setup. I'm going to select the TPS temperature platform. I do have to recheck the sensor. That's a step that you have to do. That part isn't automatic. Yeah. So I canceled the wrong experiment. So I'm going to cancel the proper experiment and copy to a new one. So here we have the asymmetric slab for 304, which has the temperature platform already selected. We do have to check that experiment. You can see stainless steel, calcium, sorry about that. We do have to check the resistance on the sensor. And next. And you'll see all of our temperature steps already set. And if we click start, now you can see the weighting, the temperature platform for that sample setup will start going to 0 degrees, and that experiment is now underway. So what I did is I canceled that. We can remove that, and now you can just see, and this was the Pyrex, so the experiment that I set up on the bench, I canceled by mistake, sorry about that. I can remove that from the schedule as well. So now we have two experimental setups underway, the stainless steel slab inside the temperature platform, and the asymmetric slab 304 running on the bench. We've already run this data, and we'll be able to review this data in the thermal analysis. So I can show you the advantages of the backing correction in a few ways. So here is Pyrex. 5 experiments of Pyrex, 20 seconds for 100 milliwatts. You could run that at different times. You could run that at 40 seconds, as long as you stay within the dimensions of your sample radially. As you could see, because of the low conductivity of Pyrex, you have some leakage, and that gives you an overestimated value of conductivity. We added another experiment, and the difference in experiment we added was known backing. So what we did was open this calculation, and I added known backing as a calculation modifier, and here's the results of that correction. So now you have about a 10 or 12% impact of that leakage in the correction for it. So now we're measuring Pyrex glass at the appropriate value in the slab module, which is very unique. That's a very unique capability, and that's because we can compensate or calculate for the heat leakage into the backing material, which in this case is XPS. And that's done through, again, modifying that experiment. So when you click backing and known backing, it opens up the ability to add in the thermal conductivity and the thermal diffusivity, which is automatic. When you pick it from the previous windows, it automatically puts those in and compensates for them. So that's Pyrex glass. The accepted value for Pyrex glass is around 1.15, so it's very good. Now we can look at another set of experiments we ran, which is PEAK, which is a polymer. It was one of the materials that I showed you. We have a little bit of a kind of a cool situation that we've measured that material on the GHFM. So here you could see the data for 40 seconds, 100 milliwatts. Why is it a different time than Pyrex? Because it's lower conductivity. So for lower conductivity materials, you can penetrate for a longer period of time because you're staying within the radial available dimensions. So 0.3 is a little high, and the corrected value, again, known backing. So we modified the calculation with known backing. This is the values of XPS, and you can see the corrected value is 0.28. And this is a screenshot from guarded heat flow meter, which is the method to the right of me, previous measurement we made, which shows you the resistance. It's a very different method. It measures a delta T across the sample, and that is the thermal conductivity, that exact piece of peak, so 0.28, compared to the corrected value of 0.28 for peaks. It's very good. Just to demonstrate the slab method in general, which does not need back-end correction. This is well within the capability of the slab method. This is a 1.5 millimeter thick piece of aluminum. It's again one of the pieces that I showed you in front of the camera earlier. We get thermal conductivity, diffusivity, and a very good specific heat. This does not need back-end correction, as you can see. We do not have to manually select the portion of time. That's automatically done by our contact correction, which measures the contact resistance and removes that portion of time automatically. That's a proprietary nature of the MP-1 TPS. You can see the bulk results because of that. And this is the residual showing the fitting and the quality of the fitting. So you can see the repeatability of less than 0.5% for conductivity. This is on aluminum 6061. So there's no input of specific heat in this case because we're well within the body of the material. Of course, you can go higher conductivity. This is copper. We ran a 0.5 second. So that was a 1 second test on approximately a 2-inch piece of 50 millimeter piece of aluminum. That's 1.5 millimeters thick. Copper is much more diffusive. It's a similar sample size. The thickness of this copper is 0.8 millimeters thick. In this case, we did enter specific heat because of probing depth limitations on the time. So here we made 0.5 second measurement. You can see our thermal conductivity and diffusivity. Entering the volumetric specific heat for these high conductivity materials corrects for the diffusivity, so we have good, accurate diffusivity results. So in both, because of that, we're able to get very good average values of a high conductivity material and a very good fitting for that same material. So this is a 0.5 second test. So the MP-1 has the ability to go from 0.5 seconds up to 1280 seconds as a time measurement. It's very important to be able to do that to measure very conductive materials. And of course, at every one of these measurements of time, we're collecting a high number of points. So at very short times, we're collecting 600 points, and at longer times, we're collecting 400 points. We have a range of times based off the shorter times. Of course, the shorter the time, the better it is to have a higher number of points we're collecting. That gives us more confidence in our data. So we've improved the recording of points with a variety of times. So here you have copper at a very high wattage with a very short time, aluminum 1 second with the same power, which we want to make sure that we're using the ITPS and the guide on selection of those parameters so that we get a nice temperature rise versus time, and our data is not full of noise. So this is our transient analysis software. So again, in previous videos, we do talk about this in depth. I'm just sort of really focused on TPS Slab, but here we have our data acquisition software that records and manages all of the experimental setups. And then our analysis software allows you to import that data and see each one. Of course, you can open up many experiments and review them all together. As the last step, let's open up that asymmetric stainless steel that we did. So that's asymmetric stainless steel 304. And what we did is open the single experiment I ran as a quick transient, the temperature rise versus time result. In advance of every measurement, it records drift, but not with a quick start. So that quick transient, rather, it's just a brief measurement, but allows us in a demonstration to show the results. Here's our residual pattern, our results once it's done calculation. And you can see for stainless steel 304, this is an asymmetric setup for stainless steel, and there's the residual pattern. So right now, that data is being run multiple times, and once that times 5 measurements is done, we can review that at another time. So that's the demonstration. There's quite a bit there, I realize, and if you have any questions, I'd be happy to answer them. If not, contact us, and we're happy to answer any questions in the future. I'll wait on for a few moments rather. So I think there's a small delay. I'll stay online on the chat board to answer any questions there as well. Thanks for your attention.